Okay, so let's start. So we continue the remaining part of chapter 6, which is about Heisenberg equation motion, for the harmonic oscillator problem. And last time we defined the Heisenberg operator, meaning the operator in the Heisenberg picture. So let me just remind you what the definition of the Heisenberg operator. Okay, so suppose this operator B at time equals 0 is the Schrödinger operator that we are familiar with. So as we mentioned last time, that we could collect all this time-dependent operator and combine this with the Schrödinger operator when we evaluate this expression value of the operator at any given time. And instead of time involving the states, we time involve the operator. Okay, so we can equally well describe this expression value. Suppose we define such an operator in the Heisenberg picture, and either we time involve the state or we time involve the operator, we will get the same result when we evaluate this expression value. But in many cases, it is very convenient and much more convenient for us to adapt the Heisenberg operator, meaning the operator in a Heisenberg picture, where the operator does time involve. And in such a case, we are able to derive the Heisenberg equation motion for the Heisenberg operator like this, where we already derive such a commutation relations and time derivative of the operator in the Heisenberg picture. And so this is the very useful equation motion for the Heisenberg operator. And this is something similar to the Newton's equation motion in classical mechanics, but here what we talk about is the time evolution of a Heisenberg operator. Okay, so we need to take the expression value or the measurement and to be compared with the experimental observations once we solve this time dependence of the Heisenberg operator. So for example, this harmonic oscillator problem, we have this Hamiltonian, but we could define this operator in the Heisenberg picture, right? So that this A and A dagger carry the time dependence. Hamiltonian itself is actually time dependent, but of course this is in the Heisenberg representation of an operator. But we know that this commutation relations between A and A dagger in the Schrödinger picture is 1, and we can also show that this is true when we consider a Heisenberg operator A of t. And so A of t, when we commute this with the A dagger, it gives us 1 as well. So this commutation relation doesn't change from the Schrödinger picture to the Heisenberg picture. So, and therefore we could simply just plug in this commutation relations between A and A dagger, also the Hamiltonian and A or A dagger, and we evaluate this very easily so that this will become the equation motion for A of t and also A dagger of t, which is these two equations. Namely, we simply just plug in this operator B of t by this A or A dagger of t and take advantage of such a commutation relation between H and A or H and A dagger that we already derived previously. And so plug in everything, you get this equation, and these two equations could be easily solved, and this is the solution of that equation. Okay, so which means that this A or A dagger operator will time evolve by this exponential factor of e to the plus or minus I omega t, where omega is the same omega in the Hamiltonian harmonic oscillator. Okay, so now things become very easy to solve because you could simply just take expression value of the A or A dagger as function of t and put it on the both sides of the equation. And since this e to the plus minus I omega t is just a number, so you simply just put the expression value on the operator itself. Okay, because we know that A and A dagger are linear combinations of x and p, right? And as a result, once we know the equation, time dependence of this A or A dagger as function of time, then we know the time dependence of this x average and also moment average. So you can actually convert this relation from this solution to these solutions easily, okay? Because we know their relations. So we simply just convert that into the variables that we are familiar with, namely the expression value of the momentum operator and expression value of the position operator as function of time in the Heisenberg picture. And then this is the solution, which means that suppose we know the expression value of x at initial time 0 and also the expression value of the momentum operator at initial time 0, then we know everything. We know how this expression value of the momentum and position operator evolve in time on average. Okay? So of course there's uncertainty relations there between x and p, but once you put this expression value here, then this makes sense because this is the solution is meaningful only if we take the expression value, which means that on average, what is the time dependence of the momentum variables and what is the time dependence of the average position operator. And this actually concludes our chapter 6. But before we end, let's just summarize this operator method in quantum mechanics. As we already pointed out, that the operator method is actually based on this Dirac notation, Brown-Cass state, and we use this operator to act down this Dirac state and lead to the eigenvalue equations. But then we could project this eigenvalue equation to the either the position eigenbasis or momentum eigenbasis. In the case of the position eigenbasis, then this kind of eigenvalue equations are precisely the Schrödinger equations that we're familiar with. For example, if the Hamiltonian is made of this kinetic energy term plus the potential energy operator, then we could use the Dirac notation to actually calculate this of energy eigenvalue equations by acting this Hamiltonian operator onto this eigenstate E. But we know that this H is made of this kinetic energy part and potential energy part. For the potential energy part, it's very easy that you could project this resulting Dirac-Cass state onto this position eigenbasis. Then you end up getting this potential function v of x times this state E, actually in the dot product with this position eigenbasis as a Dirac-Bras state. So this projection immediately tells you that this is Schrödinger wave function, right? So likewise, we could project this kind of operation where we use this momentum operator and we operated this onto the energy eigenstate E, and we simply just project this onto this position eigenbasis, and we could again play the same game that we did before, that we insert this unit matrix by expanding this unit matrix in terms of the momentum eigenbasis with the integral over dp, and then we could rewrite this in terms of the momentum operator, which is h bar over I d by dx, and times this projection between this eigenstate as a cat state and this position eigenbase is the Bragg state. So this is precisely, again, the Schrödinger wave function. So we plug in this representation back to this eigenvalue equation here, and we simply get back to the Schrödinger equation itself. Because the potential energy term is nothing but what? V of x times this wave function, right? And what about this kinetic energy term? Well, there's a p squared, which is this h bar squared divided by 2m times this second order differentiation with respect to x with a minus sign here. And times, again, the Schrödinger wave function. And if you combine this kinetic energy operator and potential energy operator, you get back to this Hamiltonian operator acting on the Schrödinger wave function, which gives you the eigenenergy E times the Schrödinger wave function. So this is precisely the Schrödinger equation, but the advantage that we use this Dirac notation is that we no longer just rely on the Schrödinger equation. So we could project this eigenvalue equation any eigenbasis we like. Okay, so the eigenstate is the eigenstate. So the eigenstate, when we project this onto this position eigenbasis, this is Schrödinger wave function, but we could project to other bases, and this will become the eigenfunctions in other eigenbases. So then we separate this, the concept of eigenstate and the Schrödinger wave functions completely. They can be the same, but they cannot, they can be different, depending on which eigenbasis that would project this eigenstate onto, right? Okay, as a final remark, as we already derived all this eigen state, eigenenergy, also this lowering operator and the raising operator in a dagger, and we know this eigenfunction at ground state U0 and the eigenenergy at ground state, which is 1/2 h bar omega, and the separation between the neighboring eigenstates in the harmonic oscillator problem is precisely h bar omega, which is a equally spaced eigenstates, and we know that this, in the Dirac notation, this at any given eigenstate of harmonic oscillator, this is given by this normalization factor times the raising operator to the power of n acting on the ground state. All right? So when we project this any arbitrary eigenstate of harmonic oscillator onto this position eigenbasis, what we get is just this Schrödinger eigenfunctions UMX, which is nothing but this kind of a expression that you take this bracket power of n and acting on the exponential function. Okay, so remember in that bracket we have the linear combinations of x and p, but p is nothing but d by dx, right? Of course, times this h bar factor, but this is the operator. This is not just a function, this is the operator, because this d by dx. So we need to take this n's power of that bracket and then try to apply to that exponential function right there. Good. So at ground state, when n is 0, you get just this exponential wave function. But when n is larger than 0, you need to take the differentiation of that exponential function, say n times. So this is a much cleverer way. So if you really carry out such a differentiation up to nth order, then you simply just reproduce this Hermite polynomial that we introduced earlier, right? So this un of x, so this is identical to this say Hermite polynomial that we derive by brute force previously. Okay, so you could very easily see that this is a much cleverer way, okay, and much faster, okay, and also provides with us more insights in terms of the physics, because once we know the ground state and we simply take the elevator to any floor we like, and then we could actually take the elevator down to any floor we like. Okay, so this, say, lowering the racing operator, this kind of concept is really useful and a necessary tools that allows us to study more complicated quantum mechanical problem. Okay, so that's the end of chapter 6. Any questions? Okay, so let's take a short break, and when we come back, we will start a new chapter, which is the angular momentum operator. Okay, so let's start a new chapter, which is about angular momentum operator in quantum mechanics. So this is a very important chapter, because in this chapter we will learn more and more this operator methods that we introduced in the chapter 6. In particular, we would like to solve the Schrödinger equation for hydrogen atom, which is a three-dimensional problem. And suppose we don't have any, say, potential, it's just kinetic energy of a Hamiltonian, but we need to solve this Schrödinger equation for a free particle in 3 dimensions. And this is also a highly non-trivial task, because this momentum is no longer just a one-dimensional variable. It's a three-dimensional thing. So you get the px, py, and pz component of the momentum operator, and where all of them are operators, right? So we know in classical mechanics that this three-dimensional motion in classical mechanics are closely related to this angular momentum quantity, which is r cross p. Even in classical mechanics, we can define this angular momentum variable as this position vector crosses the momentum vector. So in quantum mechanics, we can also define such a quantity, but remember that both r and p are no longer just classical variables, they are quantum mechanical operators, which means that this vector r as a quantum mechanical operator crosses the momentum operator. Again, the momentum operator is a vector. It's also an operator. Okay? So this angular momentum operator is a vector, but it is also an operator, which is defined as R operator crosses P operators. As a result, we need to study this eigenstates and eigenfunctions of angular momentum operator before we could try to solve this Schrödinger equation for any systems in 3D. And this is the goal of our approach, that we need to solve the Schrödinger equation in 3D, but this Hamiltonian operator consists of this kinetic energy part and potential energy part, and this both parts are three-dimensional operators. And what about this V? Well, V, this a simplest example of this potential is the Coulomb potential, right? So it's the Coulomb force that exists between any two charged particles, right? For example, in the hydrogen atom, we have, say, a single electron moving around this nucleus with charge E. So then you get the Coulomb potential between these two charged particles. And of course, there are many different types of potential, V of R, as we'll discuss later. But for the simplest possible three-dimensional potential, which is a Coulomb type, and we got sort of a central force problem. Okay, the central force problem where this potential term, V of R, of course, it is the function of this vector R, but in the central force, such as gravitational force or this Coulomb interactions in this electromagnetism, has a special property that this V of R is actually only the function of the distance between these two charged particles or between any two particles. It doesn't matter the orientation of this vector r, namely it has a spherical symmetry. And such a central force system, this potential depends only on the distance between these two objects. So in that case, we could show that the equation motion for the angular momentum operator here, dl dt, whereas the L is a vector, is also the operator, vanishes, okay, because this Hamiltonian commutes with the angular momentum operator. Okay, in such case, this angular momentum vector is actually conserved. It is a constant of time. Of course, in classical mechanics, it is easy to understand, but in quantum mechanics, we need to show that this conclusion that for a central force problem, even in the quantum mechanics, and this angular momentum vector and also an operator is a constant of time, which is conserved quantity. And in particular, we need to show that this Hamiltonian commutes with the angular momentum vector and operator. Okay, so let's do it. Let's do it. So we could consider such a central force potential in 3 dimensions. And this gradient square represents the second derivative of this wave function with respect to the, say, x, y, and z. So this is a 3-dimensional generalization of this d square. Okay, so later we will perform this change of variables from this Cartesian coordinate x, y, z to spherical coordinate r theta and phi. So we will sketch this derivation very quickly right here, but we will do it again later. So in the spherical coordinate system, we have 3 variables, r and theta and phi, right? So then along these 3 directions, we can define a unit vector. Okay, and all of the 3 unit vectors are perpendicular to each other. So yeah, so you know that, right? Okay. And in that spherical coordinate, we can rewrite this gradient square and v of r in terms of this spherical variables, r, theta, and phi. So let me just write down the final result. Here, mu is sort of a reduced mass if we consider a 2-body problem. So this mu is actually the m1, m2 divided by m1 plus m2, right? Yeah. If we consider a 2-body problem. Anyway, so it just considers mu as some mass, okay, or effective mass. And this is the gradient square in the spherical coordinate representation is given by this. Okay, so you could check either chapter 8 or a later chapter of the book that the gradient square in the spherical coordinate is given by this summation of these 2 terms. The first term depends only on this position or distance between the 2 particles, which we call this f of r. And the second term is precisely the square of the angular momentum operator. All right, so we need to derive the spherical representation of the angular momentum operator, but we know that in this Cartesian representation, which is r cross p, and which is what? ypz minus zpy and zpx minus xpz and xpy minus ypx. Right? Okay. So these are the three components of the angular momentum operator in this Cartesian coordinates. So this is Lx and this is Ly and this is Lz. So we will derive the spherical representation of this angular momentum operator later, but let's just consider this as a function of theta and phi as the angular momentum operator stands for. It only involves the angle part of the coordinates, and of course there's a 1 over r squared right here. So the second factor is precisely proportional to the square of the angular momentum operator. Okay, so let's just try to calculate this commutator between the Hamiltonian and the angular momentum vector and also operator. So in the spherical coordinates representation of the Hamiltonian, this is given by what? The f of function, right? Plus L squared divided by 2 mu r squared and L vector. Okay, so we know very well that this L commutes the L or L squared, so this term doesn't contribute. And we will see later that, of course, this f of r is a function of r, and L is a function of theta and phi, so of course they commute. So both commutator vanishes. So we're done. Okay, so this is a very elegant way of showing that this Hamiltonian in three-dimensional space commutes with the angular momentum vector L. So let me just write down the formal definition of this square, which is L dot L. Okay. So again, so we don't have time to discuss this derivation, but we will derive this spherical representation of the angular momentum vector or operator later, right? So, but this is the exact expression of L squared, which is L dot L as a vector and also as an operator. So this is an operator because you should do something, right? Because this is the differentiation of your wave function with respect to theta and also to phi. So then we show this very important conclusion that for a central force problem, and the angular momentum operator or vector is a conserved quantity, which is a constant of time. So what's the big deal? Well, you will see the big deal later. But before we come back to this conservation of angular momentum operator in 3D, so let's just derive again the commutation relations for those three components of angular momentum operators. So, because we have shown that this H commutes with L vector, which is what? Which is the three relations, meaning H commutes with all the three components of the angular momentum operator, right? Okay, So this reminds us of what? Of the commuting set. So whether all these three components of angular momentum operator and also L square and also the Hamiltonian, whether they form a commuting set. Okay, so the very important question is this: do they form commuting set or not? So when I say they, I mean Hamiltonian, L square, and Lx, Ly, and Lz. So whether these 5 different operators form a commuting set. Meaning, can we find a simultaneous eigenstate of all these 5 different operators? Okay, does that exist? The simultaneous eigenstate of all these 5 operators. Of course, the answer is no. Because some of these operators do not commute with the others. Okay, so we'll see later that Lx, Ly do not commute, Ly, Lz do not commute, Lz and Lx do not commute. Okay, so in other words, this commuting set is too big. Okay, so remember, to form a commuting set, we need to show that all of the commutators between any 2 operators in that commuting set should vanish. Okay, there's no exception. Okay, but we'll see in just a moment that this Lx, Ly, and Lz will not commute between any 2 of them. Okay, so in other words, we can choose part of them, not all of them, to be included in this commuting set. And this is very important because we need to figure out what is the maximum commuting set that we can form. And in other words, we need to figure out the simultaneous eigenstates of how many operators that we can have at the maximum level. Therefore, it is very important that we need to check the commutation relations between any 2 of these angular momentum operators. And there's another reason why we need to study first the commutation relations of all these different components of angular momentum, is that these commutation relations are really the key to actually construct the eigenstates and eigenfunctions of those operators. So as we already learned from this harmonic oscillator problem, that in order to construct this eigenstates of harmonic oscillator, and we need to define this A and A dagger, right? And study the commutation relations between A and A dagger and Hamiltonian H and A and also H and A dagger. So we need to figure out the commutation relations before we do anything. And this is the same thing, that before we do anything, we need to study their commutation relations. Okay? So in other words, one of the most important computation in quantum mechanics is the commutation relations. It's always about commutation relations, as I mentioned many, many times. So once we define the quantum mechanical operators, the first thing we need to check is the commutation relations. So now you know why we need to study those commutation relations. We take a short break. When we come back, let's just do it. Okay, so because we know the commutation relation between x and p, and the angular momentum operator is nothing but r cross p, so we should be able to study the commutation relation between any 2 of these components. Okay, so let's take a short break. 从第6章开始以后，就进入到量子力学的计算的主要的核心的部分哈，就是用运算符 operator 的方式哈，来建构这些本征态跟本征函数啊，所以我们必须要知道如何计算这些不 不同的 operator 之间的对义的关系。那所以对义的关系就是量子力学的核心的计算。我想要明白这个计算不难了哈，那但是要熟悉这个计算不简单。比如说你看我在黑板上写推导，或者是课本上的方程式，好像马上就了解是什么意思。可是你自己要做这个计算的时候，就未必如愿哈。所以很重要的一部分就是要自己动手做这些 exercise 或是一些简单的推导哈。那这些都难不倒大家哈，就是简单的微分等等哈，线性代数。好，但是这个概念需要配合这个计算，所以到这个上一章 Chapter 6开始，其实就变得没有这么简单了哈，因为这些量子力学的运算要配合你如何理解它的物理的含义哈。那所以物理的含义其实是藏在这些计算里面，对，也就是说你的数学跟物理的概念必须要结合，缺一不可哈。所以在这边就是说我需要再次强调，就是请大家务必要熟悉 Dirac 的这个表示方法哈，那熟悉 operator method， 那熟悉对义子的关系哈。Okay, so let's just derive this commutation relations between any two angular momentum operators. So let's try first Lx and Ly. As I mentioned, this could be straightforwardly just expressed in terms of x, y, z operators and also px, py, pz. And you know that this x and px, what IH bar, right? And y, and z, pz. But the other commutators are 0, for example, it's x and py, or y or px, or z and px and py are 0 when you calculate their commutators. Only x and px, 1 and p1, z and pz do not commute. Good. So then we can simply just check this commutator. Let's do it. So this is given by, right? So remember, when we calculate this commutator between a product of operators A and B and another operator C, and we could take advantage of this identity that this is given by A in the very left multiplied by commutator between B and C, and plus and C commutator multiply B on the right. Okay, so you can verify this identity very easily. So we simply just take advantage of such identity, and we separate all these commutators in this way, right? So, and we can easily see this h bar over I, y px minus xpy. Right, so the commutator between pz and z is actually minus ih bar, and this is plus ih bar. Okay, so you combine these two, you get this result. Okay, so this is precisely ih bar times Lz component, because Lz is nothing but xpy minus pypx. Okay, so we verify this general identity between any two angular momentum components when you calculate their commutation relations. Here's I and j and k are simply x, y, and z. So the epsilon ijk is actually 1 plus 1 if they follow the cyclic permutation, and minus 1 if they violate or they have some violation of this XYZ permutation. So this permutation, which says that X goes to Y and Y goes to Z and Z goes back to X. This is some kind of counterclockwise rotation, right? Or permutations. So, which means that epsilon XYZ 1, which is epsilon YZX, which is epsilon ZXY, and so on. And epsilon XZY is actually -1. Because we should have this proper order in order to get 1, but if you reverse this proper order between Y and Z, you get XZY, and there is one violation of this proper permutation, and you get factor of -1. So if you get two violations of proper ordering in permutation, you get -1 times -1, which is +1, and so on and so forth. Odd number of violations of this permutation. And this is very easy to check that this commutator between Lx and Ly is actually IH bar times Lz, which means that this is nothing but IH bar epsilon x, y, and z, Lz, and this epsilon x, y, z is actually 1. Okay, so the epsilon as a k is a tensor, right? So it's a tensor of rank 3. So define this tensor in this kind of a proper permutation. And let's just try to check the other two. So Ly, Lz, this is your exercise. And Lz, Lx commutator is given by IH bar Ly. Okay, so now you see the pattern, right? So when there are x and y components in the commutator, so you must get Lz, right? Follow this proper order of permutation, right? X, y, and z. And yz, you get x. If you start y and z, and on the right side of the equation, you get Lx. And likewise, you start from the zx. Well, what is the component on the right side? Ly, right? So xyz, yzx, and x and zxy, though they all follow this proper permutations. Okay. So in other words, you could very easily check that this commutation relations between any two components of angular momentum operator satisfy this cyclic permutation relations like this. Great. So let's try another set of commutator, which is between Lz and L square. Okay, so we could take advantage of what we have so far, which is a cyclic permutation of this commutation relations. And, well, let's just do it. This is given by Ly times Lz, Ly plus Lz, Ly, Ly, and plus Lx, Lz, Lx, plus Lz, Lx, Lx. Because Lz commutes with the Lz squared, so you don't even bother calculating this. Then you end up with these two terms, right? So of course you could use this ABC in the commutator that I just wrote here, and to separate this two commutators in terms of, say, 4 commutators, right? LZ and LX, Ly squared is actually the first one. Second is LZ and LX squared. Okay, so when we deal with the LZ commutator with the Ly squared, you simply just follow this ABC rule, and you separate this in terms of Ly on the left times LZ Ly plus LZ Ly times Ly. Okay, so but what is the LZ Ly commutator? So this is given by minus Ly LZ commutator, right? So Ly LZ commutator is given by IH bar Lx, so this is minus IH bar Lx. Okay, so this is minus IH bar Lx. Again, this is what LZ Lx, this is what IH bar Ly, and IH bar Ly. Okay, so let's just combine everything. So you get what? You get minus IH bar Ly Lx minus IH bar Lx Ly plus IH bar Lx Ly plus IH bar Ly Lx, which are cancelled exactly. So this minus IH bar Ly Lx cancelled by the plus counterparts, and these two get cancelled, and the other two right? So you get 0. Okay, which means that these two operators do commute. Okay, we discover a new vanishing commutator between this, two of these 5 operators that we just mentioned. However, you know very well that this, any 2 of this angular momentum operator do not commute. But you know that H commute with L vector, and also you know that LZ commute with L squared. Okay, so but you know that Lx does not commute with Ly, Ly does not commute with Lz, and also Lz does not commute with Lx. Okay, so what can we do, right? So what is the maximum commuting set that we can form? Of course, we cannot choose all of the 5 operators to be in the commuting set. This lesson tells us that there's only one component, which is Lz of the L vector can be in the commuting set, which means that you could only choose Lz, L squared, and Hamiltonian to be in the commuting set. This is the maximum amount of operators in the commuting set. And you cannot include Lx or Ly in this 3-operator commuting set because, as I mentioned, Lx do not commute with Lz, and Ly does not commute with Lz either. Okay, only these 3 operators commute with one another. Okay, so as a result, we have a simultaneous eigenstate of the Hamiltonian Lz and L squared. And this is very important that we will see later, that there's an eigenvalue associated with all the three operators. The eigenvalue for the Hamiltonian is the eigenenergy E, and the eigenvalue for Lz, we will see that this is m times h bar, where m is the integer number. What about L squared? Well, you get little l as the L times L plus 1, h bar squared, where L is again some integer value. In other words, we could label this simultaneous eigenstate by their eigenvalues. For example, this energy E and L, L squared, and M, Lz. But usually in the textbooks, we don't include this energy E, but just L and M. Okay, so this L represents the eigenvalues for L squared, and M stands for the eigenvalue for Lz. And when I write the eigenstate like this, this is a simultaneous eigenstate of H, Lz, and L squared. So we will come back to this in just a moment, and then we take the short break. When we come back, we will prove that we cannot add another one or two operators, such as Lx or Ly, in this commuting set. So if we do, then we violate our starting point, and the angular momentum vector will vanish altogether, which is not what we want. Okay, so let's continue. As I mentioned, we cannot add another two, say Lx and Ly, in this commuting set. But suppose we do so. Suppose there exists a simultaneous eigenstate of Lx, Ly, and Lz in the commuting set, then we'll show that all the three components of angular momentum operator vanishes. This is not what we have in the beginning. So for non-zero angular momentum vector or operator, we cannot have this Lx and Ly in the commuting set. So that's the conclusion, but we need to prove that. Okay, so let's prove. So suppose we have this simultaneous eigenstates of Lx and Ly, then we must have this eigenvalue equation where U is the simultaneous eigenstate of Lx and Ly. So we could have this eigenvalue equation of Lx and Ly acting on this U, giving rise to different eigenvalues, L1 for Lx and L2 for Ly. Okay, so let's just try to perform these two operations. Suppose I continue checking this eigenvalue equation for Lx and Ly in this order, or Ly, Lx, acting on this U, simultaneous eigenstate U, then because U is the simultaneous eigenstate of Lx and Ly, so you'll get L1, L2 for the first and L2, L1 for the second. But since little L1 and little L2 are simply the numbers, so L1, L2 is the same as L2, L1, right? As a result, you simply just subtract from another, which is Lz. Lx, Ly minus Ly, Lx, right? So you apply the Lz, you act as the Lz operator onto this simultaneous eigenstate U. What you get is what? 0. Right? Because Lx, Ly acting on U is the same as Ly, Lx, so then they just get cancelled exactly. So you get this very strange result that Lz acting on U is actually 0. But you know that this L2 times U is actually Ly acting on U. What is Ly? Ly is what? 1 over IH bar LZ LX, right? Acting on U, which is what? 1 over IH bar L1 LZ acting on U. Okay, so you simply just use this commutation relations between any two of these angular momentum operators, then you can show that this L2 times U is actually L1 times LZ acting on U divided by IH bar. But what is this? This is 0 because LZ acting on U is 0, right? So which we have already shown right here. So which means that L1 times 0 on the right hand side, which is 0. And which tells us immediately that L2 is 0. Okay? And you could also see that L1 is also 0 and L3 is also 0. In the same way that you can show, right? You simply just change the other components and check the same thing, and you'll get the conclusion that all of the 3 eigenvalues L1, L2, L3 are 0. So all of the 3 eigenvalues vanish. Okay? How can we satisfy these 3 conditions? The only way that we satisfy this is we consider a 0 angular momentum vector. Okay, so if we consider a 0 angular momentum vector, and we don't have to do anything, right? Because this is useless, right? Also, it is directly in contradiction to our starting point that you have a finite angular momentum vector. At least one component of the 3 angular momentum operators should not vanish. But since we show that all of the 3 are 0, so which means that this cannot be. Okay, and the conclusion from this kind of a proof is that we cannot include both Lx and Ly. Either one of them cannot be in the commuting set. The commuting set can only consist of the 3 operators, as I mentioned: Hamiltonian, Lz, and L squared. That's it. No more. Okay, so if we include any one of the additional angular momentum operator, and we have a trouble. Okay, the trouble is that the angular momentum vector should be 0, and which is not the case in the first place. So then we cannot contradict with ourselves in the beginning, so then we should not include any more angular momentum operators. So in the following, then we should calculate and we should do all these computations in this simultaneous eigenbasis, which is labeled by the eigenvalues of L squared and the eigenvalue of Lz. And we will do it by defining the raising and the lowering operator for the angular momentum operator. Just like what we did before in the harmonic oscillator problem, that we define the A and A dagger operator. Remember that, okay? So, and the the A operator is what we call these lowering operators, and A dagger is what we call the raising operator, because the lowering operator is actually taking us downstairs by 1 floor, and the raising operators is the elevator that takes us to the floor 1 floor above us. Okay, so it is raising and by a dagger and is lowering by a. So likewise, we could define a similar angular momentum, say raising and lowering operator. But before that, let's just define this eigenvalues little l for L squared and also m for Lz. Okay? When we act this L squared operator acting on this simultaneous eigenstate Lm, we assume that this is given by the right-hand side of the eigenvalue equation, where the eigenvalue is given by h bar squared times L plus 1. Of course, this is very strange, so why not we simply just define an eigenvalue, right? Why not the complicated product between L and L plus 1? Well, the reason why we have to assume this particular special form in the eigenvalue equation for L squared will become clear later. Okay, the reason why we assume this form. Okay, so we just to accept that assumption at this point that, of course, this will actually lead to a great simplification of a calculation. Okay, but we don't know that at this point, but we will see why we assume this particular form of this eigenvalue L times L plus 1 later. But in any case, this is some real number, right? So some positive valued eigenvalue, which is h bar squared times L plus 1. What about Lz? So when we act this Lz onto this simultaneous eigenstate, we get mh bar times L times eigenstate. So what is m? Well, we know that this is some real number, so that's it. We don't know what that is at this point. Likewise, we don't know what this L is at this point. But we will see later that both L and m could be integer values. And we could define and demand this orthogonal and normalization condition that the overlap between these two different eigenstates Lm and L prime m prime is given by the Kronecker delta function delta L prime times delta m m prime. So if any of this delta function vanishes, you get 0 because of orthogonal and normalization condition. Okay, great. So let's just define this angular momentum raising and lowering operator L plus minus, which is Lx plus or minus I Ly. So the plus refers to the raising, and the minus refers to the lowering operator. Okay, so in the following we will see the Lx is indeed the raising operator for angular momentum, because it actually raised the sum of the eigenvalues by 1 h bar if we apply this L plus onto the any simultaneous eigenstate Lm, and so is for L minus. So L minus is actually the elevator going down by 1 floor, and we will see that in just a moment. So you can see the correspondence between this angular momentum raising the lowering operator and the A dagger in harmonic oscillator problem. So they are in the spirit exactly the same. Okay, and this is what you need to learn, and this is make this operator method a powerful method, because you can always define some raising and lowering operator in any of the Hamiltonians in quantum mechanics that you could climb the stairs or take the elevators up and down until you reach the ground state, and then you construct the ground state wave functions, and you take the elevators up to all the floors, and you know everything. So that's the the trick, and that's the power. That's the advantage. And this kind of a technique is the thing that you need to learn. Okay, great. So let's take a short break. When we come back, we'll start to show the commutation relations among all operators that we just defined, including L plus, L minus, LZ, L square, and Hamiltonian. Okay, so now you can imagine that there are many, many new commutation relations that we need to worry about. So L plus, L minus, what is the commutator? And L plus, LZ, and L minus, LZ, and L plus, L square, and L minus, L square, such and such. Okay, so once we figure out the commutation relations and we know all the things that we want to know. As I mentioned, the commutation relations are the keys. Okay, it's the most important thing that we need to consider before we do anything. Okay, so let's take a short break. This is a commutator between various angular momentum operators. So first, the commutator between L plus and L minus, well, you could simply just plug in the definition of the L plus and L minus. And you know the commutation relation between Lx and Ly, and also Ly, Lx. So this is a simple task that this is given by 2h bar Lz. Okay? Good. So what about commutator between Lz and L plus minus? Well, this is given by Lz and Lx plus minus I Ly. You simply just use the cyclic permutation result for the angular momentum commutation relation. So this is given by IH bar Ly minus plus I times IH bar Lx, which is plus minus H bar L plus minus. This is very important for us to show that L plus is indeed the raising operator and L minus the lowering operator. So because of this commutation relation. So we'll see that in just a moment. And we can also verify the commutation relation between L square and L plus minus, which is 0. You can simply just use this first result and plug in the third commutator and verify that this is 0. So based on these three commutation relations, we could actually rewrite this L square in terms of L plus L minus product. Okay, so which will be used later. L plus L minus is given by Lx plus Iy times Lx minus Iy, which is L square x Ly square minus I Lx Ly commutator, which is given by L square minus Lz square plus H bar Lz. Right? So you simply just plug in the definitions of L plus and L minus in the product and try to simplify this and try to link this to the magnitude square of the angular momentum operator. And you'll find that this is L squared minus Lz squared, because this is Lx squared plus Ly squared is actually the total square of L minus Lz squared, right? And what about this commutator? Well, this commutator is IH bar Lz, which is H bar Lz right here. Likewise, we could check this product L minus L plus in this order, which is L squared minus LZ squared minus H bar LZ. So we're going to use these two relations in just a moment. So we can see that this L squared could be either expressed in terms of this L plus L minus product or L minus L plus product, right? So because both relations involve L squared in a different way. Okay, so we could just rewrite this L squared in terms of L plus L minus plus LZ squared minus H bar LZ, and also this is equal to L minus L plus LZ squared plus H bar LZ. But we know that any expression value or eigenvalue of the L squared must be positive or 0, because L is the Hermitian operator. So any Hermitian operator should have this real eigenvalues, right? Okay, but L squared should have this square of the real eigenvalues, right? So suppose L acting on some state give you some eigenvalue, whatever. But L squared should be square of this eigenvalue for Lx plus the square of the eigenvalue for Ly plus the square of the eigenvalue for Lz. Okay? As a result, you actually sum of the three squares of the real valued numbers, and the sum of the three numbers should be positive or 0. So we will use this condition later that this eigenvalues for L squared must be greater than 0 or equal to 0. So let's just try to use this matrix element or equation to actually illustrate and explain this conclusion that the expression value of the L squared sandwiched by this LM must be greater or equal to 0. Okay, and which means that since we assume that the eigenvalue for L squared is given by H bar squared times LL plus 1, so which immediately tells us that this L times L plus 1 times H bar squared must be greater than or equal to 0. Right? Okay, so this is an important conclusion so far. So we know that L should be a real number, but it could be both positive and negative. But if L is positive, then this is fine. What about if L is actually negative? So suppose L is actually less than -1 is a negative value. In that case, we could rearrange and we can redefine this L by shifting this L from the negative value to the positive value. So we can define an L prime which is minus bracket L plus 1, and L prime is actually positive. Okay, so in that case, we can show that L times L plus 1, even if the L is negative and is more than -1, L times L plus 1 is given by minus L prime times minus L prime minus 1, which is again L prime times L prime plus 1, which is again greater than or equal to 0. And this is a very strong statement saying that this L times L plus 1 as the eigenvalue of the L squared operator must be greater than or equal to 0. Okay? So even if this L is, say, less than -1, we can redefine this L and L prime so that L prime is positive and L times L plus 1 is again a positive or 0, because L times L plus 1 is the same as L prime times L prime plus 1. And L prime, in this case, is positive. As a result, the whole thing is positive or 0. Okay, so I guess that's enough for today. So next time we will see that when we act this L plus onto this simultaneous eigenstate Lm, this is given by what? M plus 1 h bar times L m plus 1. And same for L minus 1. So L minus operator, which gives you this m minus 1 times h bar. And this justifies why we call them raising and lowering operator, because suppose we are here and we applied L plus and we end up being, say, a floor above us with m plus 1 times h bar as the eigenvalue, which is 1 h bar above the starting point. Okay? And likewise, suppose we take the elevator down by 1 floor by applying L minus, and we will arrive at 1 floor below this, which is the floor characterized by this L and also m minus 1. But we don't have time to prove this, but we will prove this next time, that L plus is indeed a raising operator which raise the eigenvalue of Lz by 1 when we apply this. And L minus is a lowering operator which lower the eigenvalue and by 1 if we apply this. So this condition tells us that this L is either greater than or equal to 0. Okay, so we will take advantage of this raising and lowering operators of angular momentum vector and operator many times in the following, and then we can construct all the eigenstates based on this kind of raising and lowering operators. Okay, so let's end our lectures, makeup lectures today, and I will see you next Monday.